So I have started the live stream. You can just share your Google Slides one, right? I will just give you the information, then we can start from.
Okay,
You
my
can
screen
make
is
it.
visible, right?
Yeah.
Okay, cool.
We request you to go to the YouTube channel. We are streaming live there. There is some technical issue in this GPC. We request you to go to the YouTube application. So please, like on the chat, we have shared the. Please go to. We apologize. The YouTube link is being shared in the chat. Please switch there. We will be starting from the beginning on our YouTube channel. The YouTube link has been shared on the chat. Please go there.
Yeah, Tarun, could you please go to the Google Slide one and just share the screen and start?
Should I start?
Yeah, perfect.
Okay, fine, I'm starting.
Yeah.
Okay, am I audible?
Yeah, you are audible.
Okay. Hello everyone, I'm Tarun, and today I'm going to be talking about the mathematical foundations of neural networks. So in this talk, I'm going to be diving deep into the mathematics behind how neural networks work, because a lot of people know how to implement neural networks, but not many know exactly how these neural networks work. Right? So I'm going to be diving deep into the mathematical concepts such as matrix multiplication, gradient descent, and several other things. And I hope at the end of this talk, you have a better idea of how neural networks work, so that next time when you implement a neural network, you know exactly what's happening.
The talk has been started there. There's some problem with this thing.
Okay, so for this particular talk, I'm going to take the example of recognizing animals from images. So human beings are very good at recognizing objects from images because the human brain has been trained over several thousands of years to detect objects in images, right? So when you're born, it's like you're born with a pre-trained model, right? Thousands of years of evolution are encoded into your brain. And that's why you're so good at looking at these images and telling what's in the image, whether it's a dog or a cat or a panda, right? But for a neural network or for any machine learning algorithm, all it can see is a bunch of pixels. All it sees is a matrix of numbers. It cannot see what me and you can see, right? And recognizing objects from just a large matrix of numbers is very difficult. So we are going to be learning how we can tackle this problem using artificial intelligence, right? By mimicking the human brain. So this, I'm just going to give a little introduction to what deep learning is, right? So deep learning is just like a sub branch of machine learning, and its core algorithm is a neural network, right? A neural network is basically a weak imitation of the human brain. It's a weak imitation of biological neural networks. It's just several layers of neurons interconnected, just like how the human brain would be arranged, right? You can just imagine several neurons arranged into several hundreds of layers interconnected. And these neurons, they take information and they process it and they share it among themselves. And together, their job is to come up with an intelligent decision to some problem, right? In this case, it takes visual input from the outside world. Your neurons work together to process this image information, and together it comes up with an intelligent decision, such as detecting the object in the image, like it's a dog or a cat, right? So all neural networks do is they take vast amounts of data and they try to find these patterns and relationships using this interconnected neuron structure. Okay, so this is just a high level diagram of AI, machine learning, and deep learning. So as you can see, AI is anything that can sense or reason, right? And under AI, we have machine learning, which is any algorithm that can learn from data, right? And within machine learning, we have a sub branch called deep learning, which uses multi-layered neural structures to learn from vast amounts of data. So machine learning comprises of many algorithms like support vector machines, CAD boost, XG boost, light GBM, etc. But deep learning is different. What deep learning does is it takes vast amount of data, like image data or text data, and it learns relationships and it learns to make intelligent decisions just by looking at huge amounts of data. So this is what makes deep learning special. It learns complex human like tasks just by feeding on lots of data and finding these patterns. Okay, so this diagram seem a little complex at first, but what it's doing is actually very simple. So here, if you look at the input layer of the neural network, right, this is just a large bunch of neurons, right? It takes all the pixels of an image as input, right? Again, just to remind you, we are recognizing animals from images, right? So what we do is we take a dog image and we flatten it into a large vector. Like if we have a 28 by 28 dog image, we flatten it into 784 numbers, a 784 dimensional vector, right? And we pass this into our input layer, right? And this information is continuously processed repeatedly through the next few layers until it reaches an output, which is a dog, cat, or something else, right? So what is the processing that's happening here? So what's happening here is very simple. We we give the pixels at the input layer, and at each subsequent layer, the neural network is finding ways to combine these features to generate more and more complex and abstract features. So as you can see in the first layer, we just have raw pixel information, right? In the second layer, these raw pixels are combined and transformed to generate more complex information like curves, edges, and lines, right? And these features are again combined in the next layer to generate even more abstract features like legs, a head, and a tail. And finally, at the last layer, it combines these features again to generate something as abstract as a dog or a cat, right? And then finally, it gives us an output saying that this is a dog and not cat. So the basic idea here is that neural networks take raw input, raw sensory input like an image or text, and it continuously combines and transforms these simple features to generate more and more complex and abstract things like curves, shapes, faces, etc. And this is how a neural network goes from raw sensory input all the way to something as abstract as an animal at the output layer. So this is a general understanding of how a neural network functions, a general intuition, right? So this is an overview of what I'm going to talk about in this talk, right? There are a bunch of different components in a neural network that make a neural network work, right? That help a neural network train and learn from data, right? And each component has different mathematical concepts linked to them. Without these mathematical concepts, none of this would work. So I'm going to go step by step each part of the neural network and explain the mathematical concepts behind how they work. Okay, so the first thing is the forward propagation. right? It's how the information is propagated forward through the network from input to the output layer, right? So as you can see here, we start off with some inputs, x1, x2, and x3, right? Let's say these are some inputs. Let's say these are pixels of an image, right? And these features are combined and transformed, and we get an output at the second layer, which is y1, y2, and y3. So this is a forward propagation, right? Here I have only two layers, but a neural network can have n number of layers, even 10 or 15 layers, right? So information is and continuously transformed and combined from layer to layer to generate more and more complex features, right? So how exactly is this information processed? How do we get from the x1, x2, and x3 to y1, y2, and y3? There is something called weights, right? As you can see, every neuron in the first layer is connected to every neuron in the second layer, and every connection has a unique weight value, which is called W, right? You can see here W11, W12, W13. These are all weights, right? It's very similar to the human brain, where you have synapses, which are connections between neurons, and every synapse has some sort of weight associated with it. And these weights decide how information is propagated through the brain. Similarly, here, these weight values determine how information is propagated from the first layer to the second layer, right? So if we take y1 for example, right, it gets connected to x1, x2, and x3, right? So if we have to calculate y1, it would be x1 into w11 plus x2 into w21 plus x3 into w31, all added up, right? So as you can see here, it's just a bunch of multiplications and additions. And after this weight transformation is done, we add something called biases to the outputs. This is basically a simple vector of numbers which we add to the output vector, right? Biases help increase the representational capacity of our model and help us model more scenarios. You cannot always model a function with a simple y equals mx line. You need y equals mx plus c, right? That constant c completes a linear transformation and helps us model any straight line, right? So you might think this is just a bunch of several dozens of multiplications and additions, but all of this can be condensed and represented easily using a mathematical concept called matrix multiplication, right? Here, we can represent all the weights between layer 1 and layer 2 using a single matrix called W, right? This is the W matrix, and we multiply this weight matrix by the input vector x1, x2, and x3, right? And once we multiply the weights with the inputs, we add the bias vector. After all the matrix multiplication and vector addition, we finally come up with the output, the y vector, right? So we have just condensed a very complex process with a lot of multiplications and additions and transformations into one condensed matrix multiplication equation, right? And this is how a forward propagation works. Y equals wx plus b, where y, x, and b are vectors and w is a single matrix, right? So now we have a way to combine these inputs in a linear fashion and propagate them to the next layer. But the problem is linear transformations aren't always the best way to model a function. We need non-linearity. And that's why we use nonlinear functions called activation functions. You might have heard of sigmoid, ReLU, tanh. These are all activation functions. Here below at the bottom of the slide, I show what a sigmoid function is. It's a basic function inspired by the exponential function, which adds nonlinearity to your network. So now we perform this linear transformation, y equals wx plus b, and then we apply nonlinear function like sigmoid on this output to generate a nonlinear function. So if you keep repeating this process, linear transformation, activation function, linear transformation, activation function, you're generating a very complex layered nested function. And that's exactly what we want. the more complex our neural networks function is, it's more likely that we would be able to model any sort of data like images or text. In case you're a bit confused on how matrix multiplication or vector addition works, you can look at the examples I've given here on the right hand side of the screen, where I show how two matrices can be multiplied and how vectors can be added. But the problem here is our neural network is getting some inputs and giving some outputs. But how do we know how accurate these outputs are? What if the output is just random noise, right? So we need a way to quantify how well our model is doing. That's why we need something called a loss function. It's a function that measures how well our neural network performs on the data. It's a way of measuring the error, right? So let's say we have a neural network that outputs an output vector O1, O2, and O3. These are basically the outputs of a neural network, okay? And T1, T2, and T3 are the targets. These are the outputs that we're expecting from the model, right? So we want our output vector O to be as close as possible to the target vector T, because if the distance between these two vectors is small, that means our model is actually learning something and it's able to predict correctly, right? If an image represents a dog, you want the model to output dog and not cat, right? So the loss function is basically a way of measuring the distance between the output and the target, right? So this can be linked to the mathematical concept of distance measures, right? Let's say we have an output vector O, which is the red vector on the right hand side of the slide, and a target vector T, which is a blue vector, right? It's a blue color vector here. The difference between these two vectors, O minus T, tells you how far apart the output is from the target, right? So if O is the output and T is the target, O minus T is the distance, right? So if we calculate the length of this vector, we will get how well our model is doing, right? So one way of doing this is called the mean squared error, where we calculate the difference between our output and target, square it, and then find the average over all input samples. So this gives us the average distance between our outputs and our targets. So the lower the mean squared error, the better, because a low mean squared error means that our output and target vectors are very close together and our model is actually learning something. Another way of doing this is the mean absolute error, where you calculate the average of the absolute value instead of the average of the squared value. Both of these methods are valid and they can be used in different situations. The reason we take the square or the absolute value is because we want these distances to always be positive, right? We don't want our errors to be negative. So that's why we apply a square or an absolute value to make sure that all our distances are positive. And when we add them up, it gives us an idea of how good our model is doing, right? So now we have a way to propagate information through the neural network with the forward propagation. And we also have a way to calculate how well our model is doing through a loss function. But what's the use of a loss function if we cannot improve our neural network's performance? We know how to find out how well our model is doing, but we don't know how to improve its performance. So how do we make sure that the model is not outputting something random and it's actually learning from the data? That's why we need an optimizer. So an optimizer is basically an algorithm that uses this loss function to update the weights and biases of the neural network. So it iteratively goes through the entire data set and adjusts these weights and biases to reduce the loss function, right? Like I mentioned earlier in forward propagation, neural network is just composed of several numbers called weights and biases, and these weights and biases decide how information is propagated through the network. So we need to adjust these weights and biases in such a way that our loss function is minimized and our model actually makes intelligent predictions, right? So what we do in the beginning is we just initialize these weights and biases randomly. We just give them random values, right? Like we can say W11 equals 2, W12 equals 0.5, something like that, right? And what we do is we use something called gradient based optimization sorry, to adjust these weights. So if you look at this graph on the right hand side of the slide, let's imagine that this is the graph of a loss function. Okay, this is the graph of a loss function plotted versus the parameters of the model, which are weights and biases, right? So we know that the gradient of the loss function is the fastest way to go uphill, right? So if you're not that familiar with multivariable calculus, you just need to understand that the gradient vector is a way of calculating the rate of change of a function, right? It's like a derivative, but it's multidimensional, right? It's basically a derivative but applied to multidimensional context. So the gradient vector, which is represented by nabla j over here, represents the fastest way to go uphill. But we don't want to go uphill, we want to go down the hill because we want our loss function to reduce. So that's why the fastest way, the fastest way to go down the hill is the negative gradient, right? So that's why in gradient based optimization, all we need to do is calculate the negative gradient of the loss function and keep changing the weights and biases in that direction. If we keep moving opposite to the direction of the gradient, our loss function will keep reducing and our model's outputs will get more accurate. So as you can see here, we have calculated the gradient vector of the loss function, which is j, with respect to w and b, where w is our weights and b is our biases. You can see here the notation of partial derivatives. All we're doing here is calculating the partial derivatives of our loss function with respect to our weights and biases. And using these partial derivatives, we update our weights and biases to make sure that our loss function reduces. All of this can be summed up with this equation here on the right hand side of the slide. W equals W minus alpha into dj by dw, right? Here alpha is a small value called the learning rate, which determines how aggressively we update our weights, right? If alpha is big, that means we're aggressive. If alpha is small, that means we're being more conservative, right? And b equals b minus alpha into dj by db. So as you can see, we're moving the weights and biases in the opposite direction to the gradient, so that we're actually finding the fastest way down this loss function hill, so that our weights and biases get better and better and our model's performance improves successively as it sees more and more data. The optimizer is actually the main engine behind how a neural network learns. The optimizer is what enables the model to learn from the data and update its weights and biases. So this is all good, right? We have a way to calculate outputs, we have a way to update the weights and biases, but there's still a problem. We don't know how to efficiently calculate the gradient value, right? To do this step and optimize the weights and biases, we need the gradient of the loss function. How do we calculate this gradient in a computationally efficient way? That's why we need backpropagation. So backpropagation is basically an efficient way to calculate the gradient vector. Once we do backpropagation and get the gradient vector, we simply pass it into this optimization algorithm and it will help us update the weights and biases. So how does backpropagation work? You might be thinking that when we calculate dj by dw, we literally calculate the function completely and then calculate the derivative for each weight and each bias. That's actually not how it works. We use a very efficient and simple trick called backpropagation, where we propagate from the loss function all the way back to the input layer to calculate all these partial derivatives in a very efficient way. So as you can see here, we have three layers, X, Y, and Z. Z is the output layer. And here we finally have J, which is the loss function, right? So we use something called the chain rule, right? The chain rule is a very fundamental rule in calculus and multivariable calculus, where if you want to calculate the partial derivative of J with respect to P, where P is the list of all parameters, which is the weights and biases, you can represent this partial derivative below here as a chain product of multiple partial derivatives, right? So we can take the partial derivative of the loss function j with respect to the last layer z, and then that's dj by dz, and then dz by dy, dy by dx. As you can see here, we're moving backward from the loss function to the input layer, right? So this is very efficient because it uses matrix-based calculus instead of simple single-dimensional calculus to calculate these gradients, right? And it's been shown that this sort of backpropagation is the most efficient way to calculate vectors, calculate the gradient vector. As you can see here, I've shown how to calculate these gradients as we backpropagate through the network. If you're interested, you can look into exactly how these matrices are calculated. But the important mathematical concept you have to take away is something called the Jacobian matrix, right? Here we're not calculating the partial derivative between two numbers. We're calculating the partial derivative between vectors and matrices, right? That's why we need the Jacobian matrix. It's basically a multivariable analog to the derivative, where if you have a vector with called A and a vector called B with components A1, A2, and B1, B2, the Jacobian matrix has all combinations and permutations of the derivatives of A with respect to B. So A1 by B1, A2 by B1, A1 by B2, and so on. So using Jacobian matrices and backpropagation and the chain rule, we can actually calculate this gradient vector dj by dp in a very efficient way, thereby allowing our optimizer to adjust the weights and biases. Okay, cool. So now we have an entire setup where we can propagate inputs, get an output, and even train our network to reduce the loss function. But we still have one problem left, which is overfitting. Overfitting is when your model memorizes the data instead of actually finding relationships, right? So the neural network does very well on training data, but it fails to perform well on unseen data. So if you give an image of a dog that it's never ever seen before, it's very likely that it will fail, right? So so to combat overfitting, we need to reduce the power of the model. We need to reduce its representational capacity. How would you do that? We can use something called dropout, right? As I've mentioned here, dropout is a way of randomly ignoring neurons in a neural network layer so that the model's capacity or the model's complexity reduces. When the model's complexity reduces, it's actually forced to learn representations instead of memorizing facts about the data, right? Dropout actually helps the neural network's neurons work together more effectively and combat overfitting by reducing the computational complexity of the model, right? So dropout, and the other way of reducing overfitting is L1 and L2 regularization, where we penalize the model if it adjusts the weights and biases too much, right? So we do this by adding a regularization term to the cost function, right? So as you can see here on the right hand side of the diagram, we have two weight vectors, the red weight vector and the green weight vector. The red weight vector is very big. That means the model has adjusted it a lot. We are going to penalize this and make sure the model does not adjust the weights too much. Why? Because if the model is adjusting the weights too much, that means it's fitting too closely to the training data and it's not actually learning representations, right? So if you can see below on the bottom of the screen here, we're adding a regularization term, 1 by k times L square norm of W. So the L square norm of W is basically the size of these W vectors. So when we add this regularization term, the model is forced to not overfit. It's forced to reduce the magnitudes of these weight vectors and not closely fit the data. This makes sure it actually learns representations. So using this concept of L2 norms, we can successfully reduce overfitting. So this comes to the end of the main content of my talk. Just to recap, we have the forward propagation, which is matrix multiplication vector addition. It helps us propagate information through the neural network. Then we have a loss function, which helps us calculate the distance between the output and the target using distance measures. We have an optimizer that uses gradient based optimization to adjust the weights and biases of a neural network to get better and better accuracy. We have backpropagation, which uses Jacobian matrices, gradient vectors, and the chain rule to efficiently compute these gradients and enable the optimizer to make updates. And finally, we have regularization, which uses distance measures to successfully combat overfitting and make sure a model generalizes to new data easily. So these same concepts that I taught you today about matrix multiplication, Jacobian vectors, etc., they're a very general way, they're a very general framework which can be applied to almost anything in AI, right? We can use these same concepts of backpropagation and forward propagation and weights and biases to build specialized architectures for language and vision problems. For example, for natural language processing, NLP, we have RNNs, we have LSTMs, we have transformers like BERT and Roberta. All of these models share a lot of similar concepts with the classic vanilla neural network, which I explained today, right? Text sentiment classification, automated question answering, conversational chatbots, all of these advanced technologies use the basic concepts of backpropagation and optimization. And then we have computer vision, where we have CNNs and capsule networks, etc. You can use this for product anomaly detection, lung and skin disease diagnosis, automatic image segmentation for e-commerce, and several other amazing applications. So this general framework of a neural network can be specialized and changed for your specific problems. And this is what makes neural networks so powerful. It's a single framework of mathematics that allows you to almost solve any problem just using a vast amount of data. All you need to do is build a good neural network architecture, throw in lots of data, and you have an intelligent algorithm that can solve a lot of your problems. And on that note, I finish. Any questions that anyone has, I can
Yeah,
answer.
definitely. Yeah. So, Tarun, first of all, thank you so much for your insightful talk. Though there was some like technical glitches at the beginning, but yeah, we managed it. So thanks to you too. And we have a few questions like Rakshit Sakhuja is asking, what's full form of TSE? Is it total squared error?
Wait, I can't hear you. Can you repeat that again? Your audio is breaking a bit.
Okay. So what's the full form of TSE? Is it total squared error?
TSC.
Okay. So, like, would you love to speak something, or would you love to share your insights on TSE a bit, like 1 or 2 minutes on that topic, if you want?
Um, I'm not able to hear you. Your voice is breaking a lot. Can you say it again?
Okay. So could you please go into the chat of this Streamyard? I will just type it there.
Okay. Okay, I'll just answer some of the questions here.
Like, you may also view that in the chat window, right? YouTube chat.
Okay, so I'll just pick up random questions in the chat and try to answer them.
Definitely.
Okay, so I can see a lot of questions here. I'll just try to answer some of them. So, what's the full form of TSE? Is it total squared error? Yes, TSE is total squared error. Basically, all you do is calculate the squared error for each sample and then sum all of them up. That's a total squared error. MSE is mean squared error, where you sum up all the squared errors and then you divide it by the number of samples. So that's the difference between TSE and MSE. I hope that answers the question. Um, okay. So where can we get the slides of this lecture? I think the slides will be shared on Kaggle
GitHub.
Days Meetup, Delhi NCR's GitHub,
Yeah.
right? Okay, so can you say how dropout reduces overfitting? If some of the neurons are dropped randomly, won't it affect the model? Okay, so if neurons are dropped randomly, the point is that it effectively reduces the complexity of the model, right? And it forces every single neuron in the neural network's layer to learn something, right? If we do not drop any neurons, then some neurons will learn a lot and some neurons won't learn anything, right? It's like if you're in an organization, right? There are some key employees and there are some employees who don't contribute anything, right? So if you fire the top employees, the lesser contributing employees are forced to learn something and they're forced to contribute, right? So if you keep dropping neurons randomly, you're forcing every single neuron to learn something, right? And so then the entire burden is not put on specific neurons. That makes sure that your model is more robust and it does better on data that it's never seen before. I hope that answers. Is it that we ignore a neuron if its activation value falls below the threshold? If so, how is the threshold decided? Okay, so there's an activation function called ReLU where we drop every activation that's below zero and we leave every activation that's positive, right? So in the case of ReLU, we set the threshold to zero and we dropped every activation that's below zero, right? But in other activation functions like sigmoid and tanh, it's a perfectly smooth activation function where we do not ignore any activations. So it depends completely on the activation function. Okay. How does L1 and L2 regularization impact our results? So what L1, I think I'll just go back to the slide maybe. L1 and L2 regularization, basically what they do is they make sure that the weights and biases in our neural network are not updated too much. They do not move too far away from zero. Why? Because if we do not put constraints on our neural network to reduce the updates, then our model will just overfit to the training data and it won't learn any general ideas or general representations. That's why we add a regularization term to make sure our model doesn't memorize. So if we keep these weight and bias vectors small, right, instead of updating them too much, then our model will be more robust and it will do better on data that's never seen before. It will be more generalizable. Okay. Okay. So I think there's two more questions. Please explain why use kernel initializer and bias initializer in neural network. Because when you're training a neural network, you do not know what the weights are in the beginning. So you need to initialize with some random values, or you need to initialize using some random distribution, like a normal distribution or a uniform distribution. That's why we need to initialize the kernels and biases in our neural. Okay. So how for reducing model complexity, why not prune the model? Actually, this is a very new thing. Proving the model is definitely a good idea, but that's not always an option. Sometimes you want to use dropout because you don't need to change the model or change any connections in the model to implement dropout. So sometimes it's much simpler to implement dropout instead of trying to prune the model, right? Um, while predicting a value,
Yeah, Tarun, like,
hear me?
Tarun, you
Am I
can
audible?
continue. Yeah, yeah, yeah. Your audio break in the midway, so now it's audible.
Okay, so you're asking why predicting a value using DeepNet, which optimizers can be used? In classification problems, Adam is preferred most. Is it the same for regression tasks? So the optimizer you use is very specific to the problem that you're trying to solve, right? In some cases, you might want to use Atom optimizer. Some cases, you might want to use SGD or RMS prop. I think it completely depends on the problem. You need to experiment with different optimizers and learning rates until you get a model that converts properly and does well on unseen data. So I think it's more of a question of experimentation. But yes, I've seen Atom is very common for classification tasks. It seems to perform very well and avoid local minima better than SGD in many cases. Okay. So is dropout only applied while training or both while training and testing? So dropout is only for training because we apply dropout so that our neurons are trained properly. We don't need to apply dropout during testing. We just let all the neurons keep their activations because we don't need it while testing. It's only for training. Okay. Can you explain vanishing and exploding gradients? Okay, so vanishing gradients is when it's a problem with backpropagation. When your neural network is too deep, right, and your gradients are less than 1. Let's say all your gradients are 0.5. If you keep multiplying 0.5 again and again and again using the chain rule, your gradients will become so small that your neural network won't update at all, right? If I multiply 0.5 into 0.5 into 0.5 into 0.5 10 times, the gradient is almost zero. So that's what vanishing gradient is. Exploding gradient is when all your all your gradients are so big, like 2 or 3, and they're continuously multiplied. So you're seeing an exponential growth. 2 into 2 into 2 into 2 multiplied 10 times will give you a massive gradient, and that will make the model go haywire. It won't learn anything. It will just update its weights randomly. So there are a lot of ways to solve vanishing and exploding gradients, right? One way is to use adaptive learning rates, like in certain optimizers like Adam. Another way is to build shallow neural networks so that you don't have the problem of several gradients being multiplied. So instead of a 10-layer neural network, you can use a 2 or 3 layer neural network. Okay. How can we detect the neurons?
So this would
I'm
be the
not.
last question. Like this would be the last question. After that, like we would be welcoming Tanul for his talk. Okay. So like
Okay.
this will
Okay.
be the last.
So one last question. So, how do we decide on values that we pass as part of L1 and L2 regularization parameter? Okay, this is the last question I'm answering. I don't think there's time to answer any more question. So, if you're using PyTorch, all you need to do is add a term to your loss function, which has the sum of the squares of the weights, right? So basically, L2 regularization is when you add a fraction of the sum of the squares to your loss function. That will penalize your model when it updates the weights to too big or too small values, and it keeps them close to zero. So all you need to do is calculate the sum of the squares of the weights and multiply that by small hyperparameter beta, which is let's say 0.01, and add that to your loss function. For L1 regularization, you need to sum up the absolute values instead of the squares, right? So you sum up for L1 regularization, you take the absolute values of the weights, you sum them up, multiply them by the beta coefficient, and add it to your loss function. So it's very easy to implement it by hand. If you're doing with PyTorch, I'm not sure how you would do it specifically with Keras or TensorFlow. But with PyTorch, it's very simple. So I think that's the last question.
Yeah.
Thanks everyone for attending. I had a lot of fun giving this talk. I hope you all taken away something that you didn't know before this talk and you're confident with how neural networks work. So next time when you say model.fit, you know exactly what's happening.
Exactly. So Tarun, thank you so much for your insightful talk. Like we at least like we now know the mathematics behind those things that we use. Usually in real world, we usually type in the things and we miss out the mathematics section of those things. So I think that your talk would be addition to that. Like we would be able to analyze the things, the mathematical foundations, like your talks title, right? So it aptly justifies that. And thank you so much for taking out time and stay safe and take care of your health, buddy. And thanks. So like it was really a pleasure to host you, right?
Yeah. Thank you so much for having me on this. It was a lot of fun, and I hope I could spread some useful information to everyone.
Thank you so much. Thank you. So Tanul, Tanul, are you there? Like, could you please unmute and introduce yourself?
Hey,
And
hi
and
everyone. I
and
hope I'm audible. Uh,
and Tarun, could you please mute yourself so that like the voice don't clash? Yeah, sure. Thank you, Tarun. Yeah, Tanul.
yeah, so hi everyone. My name is Tanul Singh, also known by the name Mr. Know Nothing on Kaggle. Uh, I'm here to present my talk on introduction to transformers. Like I know this is a very recent topic and it's kind of a tough topic which I have chosen, but the transformers are very close to me and I've been working a lot with them. So I thought, why not share it with everyone on Kaggle Days community. So thanks for tuning in. Without wasting any time, I'll just start with the talk if that's okay, Ion.
Yeah, sure. You can move ahead and do click that hide button so that it doesn't pops up, right?
Yeah, okay.
Like, yeah, below transformers.
Yeah, so I'll this will be more of a visual treat, and there is a very less amount of things written in the PPT. I'll be speaking most of the things, so I hope you enjoy the presentation. The main point being the things which I am going to explain is mostly my interpretation and what I have learned. I might be wrong at points, but to the best of my knowledge, I've tried to convey everything which I have learned from about the transformers, so that every one of you can understand. So let's begin. Introduction to transformers. Attention is all we need right now to make you understand what transformers are. So a little about me. Why would you listen to me? Like it was February when I was like you on the other side, and I had 0 Kaggle medals, and now it is July 11th, and you can have a look at the screen, and it's me. So if you think I'm worth listening to, uh, so yeah, you can listen to me. And so the plan of attack for today will be like, you cannot go to the transformers without understanding the basics, and I found it more intriguing and intuitive once we know the basic concepts of RNNs, sequence to sequence models, and how attention work with sequence to sequence models, because transformer are basically an adaptation of the attention mechanism. So yeah, first we'll know what RNNs are, what are their types, then what are sequence to sequence models, then sequence to sequence with attention, and then we'll move on to the transformers. So let's begin. So first is RNNs and their types. So if you all have a good understanding of what RNNs are, you might know that we have a single RNN block. We feed a sequence to it, and it pops open and takes in sequence one by one. So there are basically 5 type of RNNs, and the first is one to one, when we have a single input and we want a single output, right? Then we have one to many, like when we have a single input, a single word, maybe a single thing, but we have a series of output that we want from it, like in audio generation. And then we have many to one. We have a lot of, like we have a sequence of some length, some finite length, and then we want just a single output. Then there are 2 types of many to many networks. Like first is when we have like a sequence which is having more than one which is having more than one length, and then we have output as a sequence too. But in this case, like in many to many one, we have different lengths for the input sequence and for the output sequence. We can also have a many to many network in which we can have equal lengths for the input sequence and the output sequence. So what we are going to be focused at right now is many to many network in which the lengths are different, meaning the input sequence has a different length and the output sequence has a different length. So these are also known as sequence to sequence models, and also commonly known as encoder decoder architecture. and that is the basic part of a transformer. That is where the transformer's roots lie upon. So these are the basic types that you needed to understand before going further. Now we'll try to understand what is a sequence to sequence model and what is actually the encoder decoder type architecture. So like you can see the figure here, it represents a sequence to sequence model. What we have is we have a first word in the sequence, then the second word in the sequence, then the third, and then the fourth. We have two structures. One is called the encoder and the other is called the decoder. Now since we have different input and output lengths, like we can have length of the input as 4 or 5 or 6, whereas the length of the decoder can be 1, 2, or anything more than or even less than the input sequence. So for these type of problems, we need a architecture called the encoder decoder architecture. The encoder is basically, an LSTM or RNN or any bidirectional RNN, anything which you want. And the decoder is also it can be a stack of LSTM, RNN, GRUs, anything you want. So what we do is we input the input sequence through an embedding layer. We pass it through the first encoder stack, which is obviously LSTM stack or GRU stack. What we do is we neglect the output of all at every time step. We neglect the hidden state at every time step. And what we do is we just take the hidden state of the last time step and we pass it to the decoder. If you are familiar with RNN, we always start with initial initial random weight when at the 0th step of the RNN, right? But with decoder, what we do, instead of starting with a random weight, we use the last hidden state of the encoder as an input to the first time step of the decoder. So that is the only change, and then we try to predict the output sequence which we wanted. So this decoder and encoder architecture can be trained in two ways. First is the simple way, like we train a language model. We have a just a start token. We want to predict what is the first word. Then we sample the best, like say n words, and we transfer it as an input to the next step of the decoder. And then we repeat the process as we do in a language modeling task to get the outputs. This is one way. Another way is known as teacher forcing. In that, what we do, instead of taking the output of the decoder and giving it input to the decoder in the next time step, what we do is we give the input the original text, like how are you is the question, and we want I am good as the answer. So the first token will be the same start token as before, because we want to offset uh, the output sequence by 1. So the second input to the decoder will be I instead of the sampled output from the decoder output. So the second input will be I instead of supplying the output from the previous time step. And again, the input to the second time step will be am, and then we can repeat the process. This is known as teacher forcing, where we are forcing the model to know what the next words are, and then the model works better. So these are the two ways in which the encoder decoder model architecture can be trained. Now before yeah so these encoder decoder model architecture can be used for question answering, for machine translation. Before transformers came out, these were extensively used. So what was the problem with these, so that we had to develop a new architecture? So the problem was neglecting long-term dependencies. As we can see, we are only taking the last hidden state of the encoder architecture, and we are neglecting the information from all the previous states. We are not taking into uh, accommodation any of the previous information, like what what really how has to do with the output, what really r has to do with the output, what really u has to do with the output. What we are doing is we are just taking an equivalent kind of a embedding which we feed into the decoder, which tries to get the context of all the words at once, which is obviously not the right thing to do. The sequence and sequence model uses only the last hidden state of the encoder block, and thereby discarding all the other information, right? And the output sequence which we have from the encoder, so the output sequence which we are going to predict is now totally heavily dependent upon the context which is defined by the last hidden state of the encoder, right? I know there are too many jargons. I'll try to, just bear with me, you will understand everything. So the main part is we are taking only the last state of the encoder, and that we are thinking that it will take the context of all the previous words. So our output is totally dependent on that single input, and we do not know whether it is correctly taking all the context or not. So yeah, when the problem was seen that whenever we got to very long sentences, the single vector at the end of the encoder was not able to take all of the things in the context. So we needed a solution. So what was the solution? The solution was attention please. And obviously, when the last hidden state was not able to get all the context, what we decided to do was to use all the hidden states of the decoder. Instead of using just a single state, now we use all the hidden states of the decoder. The problem with all using all the hidden states of the decoder is like not all the words, yeah, not all the hidden states might be useful for us. So instead what we did was to give relative weights to different state of the encoder while predicting the output. It's similar to human intuition, like when we read a sentence, we know, like a cat is sitting a cat is sitting on the wall, it is going to jump. When we say it, we know that it is referring to the cat. So we are able to attend to a previous word when referring to a future word. That is the whole intuition behind this. Like when we predict the first word of the output, can we look back at the word which is referring to? If we can, then we can match the human level performance, right? Because that's what a human does. So while we are doing this, this is the main intuition behind it. We want the model to attend to specific words which are responsible for this translation or for this output to take place. Now, as we know why we are using attention and what was the solution, I'll try to explain how do we incorporate attention in sequence to sequence models and how do we use it, because that is the basic necessary point for understanding the transformers. Yeah, so this is my understanding of what attention would look like when we are using a simple sequence to sequence model. There is not actually an attention block present, but I have just visualize it to just make you understand better. So let's take an example. As told earlier, any sequence to sequence model will contain an encoder, a decoder. So we have that here. One extra thing that we have is an attention block. So in the last in previous sequence to sequence model, what we did was just take the last layer, last hidden state, and transfer it to the decoder. Instead, we pass the input I am Tanul Singh to the encoder. It encodes, like it passes it through the LSTM RNN stack, whatever we have. We take the encoder hidden state at every time step. Like we take the encoder hidden state when I is when we are inputting am, we are taking the first hidden state. Then when we are inputting Tanul, we are taking the second hidden state. Then when we are inputting Singh, third hidden state, and then the fourth hidden state. So in this case, the encoder hidden state are 4 in number. So I'll just write it down. So we have 4 encoder hidden state, and we just transfer it to the attention block. Now we have the decoder. We have the first the input sequence, the start of sentence, and then we have the translated I translated into J, which is Italian. So now what we do, let's say we are at the nth time step, which is predicting J. We take the decoder hidden state at that nth time step and we transfer it to the attention block along with the four hidden state of the encoder. And the decoder output at the hidden state is transferred to this concatenation layer. So two things are happening. Like for the nth hidden state, n could be any time step. Like in our case, it is we are trying to predict the second word or the first word actually, because first was actually the beginning of the sentence. So the first, it is our first time step. So we transfer the decoder hidden state to the attention block. We transport the decoder output to the concatenation layer. Now what an attention block does is it takes the four hidden state from the encoder and the one hidden state from the decoder. It does something, it cooks up something in this black box, and then it outputs the context vector for that time step, which is first in our case. So again, we pass the first word. We have a decoder output and a decoder hidden state. We transfer the decoder hidden state to the attention block. We transfer the decoder output to the concatenation layer. We take the encoder hidden state at each time step. We pass it to the attention layer. The attention block does something under the black box, and what it spits out is a context vector for the first time step. In the concatenation layer, we will now take the context vector and the decoder output at the nth time step, and then we'll concatenate it and then pass it through a feed forward neural network to get our output. Now this way, when we are trying to predict the first word like J, we can have a look at every word from the encoder. Like we can look at I, we can look at M, we can look at Tanul, and we can look at Singh. The context vector is basically saying where should I look the most. If the context vector has a very high value for I, it is saying please don't look at any other word, just look at I, and it should be the main thing to just transform it into J. If the context vector has a high weight for Tanul, it is saying that don't look at anywhere, don't look anywhere else. Tanul is the main word which is being referred, which is to be taken into consideration for the output of this particular time step. I hope it is clear, because this is the key to everything. If this is understood, everything from this point will be a piece of cake. So again, the main intuition was to look at every word while predicting a word, a single word like J. So that was the main intuition. Now we can pop out the attention block and see what the hell is going on inside it. So let's have a look. So peeking into the attention block again, these are not actually the layers. We have nothing like this. I'm just visualizing it for better understanding. So as when I was learning, I was having a very difficult time on understanding attention block. So what I did is just to break it down into layered network like we do in transformers. So basically what my attention block would consist of will be an alignment layer, an attention weights layer, and a context generation layer, right? So as we know that the input to the attention block is all the hidden states of the encoder, which is 4 in our case, nth hidden state of the decoder, n is 1 here, the first hidden state of the decoder. Then we pass it first to the alignment layer. What is the alignment layer doing? So alignment layer takes all of the hidden states of the encoder and the first hidden state of the decoder, and it somehow calculates an alignment score for each of the hidden state of encoder. Now if we can say like we have first hidden layer, second hidden layer, third hidden layer, and fourth hidden layer, all stacked in a matrix like this. And we have the nth decoder output. So we somehow use these information to calculate an alignment score for each of these hidden layers: 1, 2, 3, and 4. And Ion, are anything which I'm typing on the screen, are these visible?
Yeah, these will be visible to the YouTube live too. Yeah, everything
Okay,
is
okay.
being shared.
Yeah, so when now we have the alignment score for first hidden state of the encoder, second hidden state of the encoder, third hidden state, and similarly fourth hidden state of it. Now we pass this alignment score to the attention weights layer, where we really get the weights of to which hidden state of the encoder we want to give the most attention, or to which hidden state of the encoder we want to give the least attention. How are these weights? How are these weights calculated? Is just we just take the softmax of the alignment score to calculate the attention weights. Now these attention weights is sent to the context generation layer, and it does something, and again it calculates the output vector for the nth time step. So we have popped open the attention block. It takes in all the hidden states of the encoder, nth hidden state of the decoder, calculates an alignment score in the alignment layer, passes it through the attention to the attention weights layer, calculate the attention weights, passes it to the context generation layer, and then outputs a context vector for the nth time step. Now we'll look at the all the layers one by one. Let's start with the alignment layer. So this is the most important part. Yeah, so as explained earlier, the inputs are still the same. What we do is we stack all the hidden layers as a matrix. Like, let's say h1, if h1 is the first hidden layer, h1 will be stacked like this, and similarly we will stack h2 and h3. So this is a matrix of stacked hidden layers, and this is the nth state of the decoder, which we have transposed to be a row vector like this. What happens in the alignment layer? Now, as I told, we take this and this information to calculate the alignment score. So one, I like to introduce you to some notations which will be helpful for us when discussing transformers. The nth decoder output, which is input to the alignment layer, is also called a query. So this thing here, right here, is also called a query. The
Tanul,
intuition is,
so
yeah,
yeah. So Tanul, could you please use a different color? Maybe like it's
yeah, yeah, sure,
getting mixed with it. So
sure,
be yellow or be it black, so that people can understand.
yeah, yeah. Sorry.
Yeah, no worries. It works.
Yeah, so we will have, let's say, first hidden layer stacked, then in a column, then the second hidden layer, and the third hidden layer. So basically the columns will be number of hidden layers, which is 4, and the rows will be the embedding size. Let's say it is 512. I know why this is happening. I'll take white. Let's say it is, yeah, so let's say just it is the embedding, like the row is 512. We have an embedding layer which spits out 512 character 512 dimensional vector. So yeah, the intuition is that we are predicting the word n, we are querying that we are predicting this word, what should I look at? So that's why it is called a query. Like we have this, it is saying to the decoder is saying to the encoder, man, I have a query, I am predicting this word, please can you tell me which word should I look at? And the encoder and the attention layer says, okay man, I'll just give you a context vector so that you can help yourself. So that is the main intuition. For every encoder state, like for every encoder hidden state, in our case the encoder hidden states are 4. These are also called keys. So the encoder hidden states uh, we take two things out of them. One is called the keys and one is called the value. They both are exactly the hidden state encoder, and we just copy this matrix into two different things. One is called a key and one is called a query. Sorry, one is called a key and one is called a value, and I will explain it later. So now for getting an alignment score, as it said here, we use any function f which takes in queries and keys. So the function can be of three types: a simple dot product of this vector and this matrix, a weighted dot product in which we take the dot product and we also multiply it with a weight which is trainable. This is called multiplicative function. Then we also have a additive function, which is a whole complex process. But since in encoder since in transformers also we use simple dot product, so I'll do the same here. We will assume that our function f is just a simple dot product of query and keys. So we have this vector and we have this matrix. We just do the simple dot product here, and we get vector containing alignment score of all hidden state. The size will be 1. Again, one thing more, the embedding that we generate in the decoder and the encoder should be the same. So 1 comma 512. I'm not good at using these things, so please pardon. And this will be 512 comma 4. So we'll have a vector which is 1 comma 4. So we have an alignment score for every every hidden state of the encoder. That's all what we wanted. So this is basically the alignment layer is doing, and I hope that is now clear to you, so that we can move on to the next layers. So the last two layers, the attention weight layer and the context layers. So we have the alignment score, as said earlier, of shape 1 comma embedding size. The attention weight layer does nothing. It just takes the softmax along the axis and just outputs the attention weights. So the attention weights are of the same size, 1 comma embedding size. Now the main part, how to generate the context vectors. Now we have the attention weights, right? We have the attention weights for first hidden layer, for second hidden layer, for third hidden layer, and for fourth hidden layer, right? Now what we want to do, we want to take the attention weight of the first hidden layer, take the first hidden layer, like we will have 512 values for first hidden layer, right? Because the embedding was that way. We multiply the weight, the first weight, to every element of this hidden layer, and we add them to get a single value, which is the first context vector. So basically what we are doing it again, we are taking this alignment score vector like this. We have a matrix in which we had stacked all the hidden layers 1, 2, 3, and 4. In the previous case, it was called keys. Here, these are called values, although they are the same thing. We multiply these two and we get the context vector, right? So this is basically how we get the context vector. This is the easiest way I can think of, and this is the way I understood it. I hope I'm clear in explaining. So this does the job. The encoder says, hey man, take this context vector. I hope it is clear to you. The decoder says thank you, and then it incorporates it and prints out the output. This is how attention works with sequence to sequence models. And it gave a very big boost, as we were now, it was now having a fairly human level intuition. Now it can look at previous words to predict what should be the next word, right? So why did we need the transformers then? So every time we have a problem, we need to have a solution. But right now, as of now, we cannot see any problems, right? But there was a problem, and we should discuss that. So here Bumblebee is asking, can my brothers solve my speaking problem? Bro, yes, I guess they can in the future if you exist. So what transformers brought into picture. They removed LSTMs, GRUs completely from the encoder decoder network, right? What we were doing in encoder, we were stacking LSTMs, and in the decoder also we were stacking LSTMs or GRUs. But transformers, Google said, man, I don't think I need anything other than attention. That's why the paper is called Attention is All We Need. So it said, I'll remove all the LSTMs, GRUs. Why? Because when we are inputting to an LSTM or an GRU, which is a sequential network, right? We first take the first word, calculate something, and then the second word, calculate something, then the third word. The story continues. So it is a sequential thing. We cannot parallelize this kind of thing, right? When we have a lot of big models and a lot of a lot of data, we cannot use it effectively, and you know how much data Google has, so it had to find a solution to remove the complexity. So yeah, Google said hold my beer, and there came the transformers. So they removed LSTMs, they removed GRUs completely from encoder decoder network to counter the problem of slow speed due to their sequential nature. And instead of these LSTMs and GRUs, they introduced a new concept, which is a very interesting and very good concept known as self-attention. The whole architecture, this transformers, is based on attention and feed-forward neural network, thus removing the sequential nature. And we can, these transformer models can be parallelized, like they can be easily parallelized, and we can, the speed is top notch, and we can use it effectively. They introduced another thing to multi-headed attention. Why? We will discuss later. They introduced positional encodings. Why? Again, we will discuss later. So the problem with sequence-to-sequence attention was it was too slow. We were not able to parallelize it, and that the solution to which came from the transformers, which is just attention. Now let's look at the transformer. So when Bumblebee goes into the car form, it looks like this: a simple encoder decoder. When when it unleashes itself, it's this beast right here on the right side. And don't be afraid, it will be easy. Jay Alamar has already helped us to understand this. So let's say the transformer is same thing. We have an encoder, we have a decoder. We pop open the encoder. What we see this very complicated structure. Now let's forget the add and norm for this moment. Let's say it doesn't exist. Let's say this add and norm doesn't exist. Let's say this doesn't exist, and now we focus on the encoder block, right? We only have a multi-head attention, which is something we don't know, and a feed forward neural network. So encoder is basically a feed forward neural network and a multi-head attention, right? Now let's look at the decoder too. Add a norm, we cut out, add a norm, cut out, add a norm, cut out. And now we see. So we have the same thing, multi-head attention. We have a multi-head attention in which you can see an input is coming from the encoder, right? Similar to thing that we had in the sequence to sequence attention, right? We transferred the encoder hidden state to do some kind of attention. So this is similar to that, as we will understand later. And then we have a feed forward. So this is the easiest part. Now we will look at them one by one to understand what is really going on. Yeah. So the plan of attack is, again, first we'll look at encoder and self-attention, then we'll multi-headed attention, positional encoding, decoder, and then we'll look at transformer as a whole. So let's start with encoder and decoder. I hope I am visible. So yeah, as we can see here, we have encoder, which is again a self-attention and a feed forward, right? So how this works is, what is self-attention actually? So we learned about attention, right? We had a query, we had a key, and we had a value. What we did is we took the query, which was coming from the decoder. We found the alignment score with the key. We generated a attention weight. We multiplied it with the value, and we got whatever we wanted, right? The context vector. Here, we do not take the query, from the decoder, right? Because it is self attention. Self is the keyword here. What we do is every thing which is coming to the encoder, yeah, the sequence which we have in the encoder, right? It is itself the query, because it is self attention. Everything which is input to the encoder is the query itself. Because every time we want to do self attention, what we are saying is, uh, why cannot I look at all the information that is presented to me, and then I'll try to have a context of whether this word is related to this word. Like, for example, the cat is, like, let's say the input to the transformer encoder is the cat is sitting on the wall, it is drinking milk. So the encoder tries to understand what is it looking to. So when we are using self attention, we are having attention weight for it. Like, when we are predicting it, we will have attention weights for all the inputs that we have. So the encoder knows what the context of the word is with respect to the input sentence also. So the self attention is basically saying, I also want to look at what my input is, rather than trying to look at only what to predict at the output. So this was a much better way, and it let's look at how it's done. So this is the main point here. As we now know that we do not have an LSTM or a GRU, so we do not have any kind of hidden states, right? So how do we find the queries, and how do we find the keys? How do we find the values when we do not have any hidden states, right? So what they did, they took a weight called query weight, query key, and sorry, a query weight, key weight, and a value weight, right? Let's say the input is thinking machines. We'll have an embedding layer which will embed it into some kind of n-dimensional vector. We have this vector. Now we have a weight for query. We multiply this x1 with this wq to get q1, right? Since we do not have LSTM, we use weights instead of using uh, the hidden states that we used. We are now using weights. That's the simple difference here only. So we multiply x1 with wq, we find the queries. We multiply x2 with wq, we find the queries. As said earlier, since this is self attention, every word which is input is a query. So we'll have a query for every word. Again, we multiply x1 with wk to find the keys. We multiply machines and x2 with wk to find the keys, and similarly we find the values, right? And these weights are not trainable. When we train the transformer model, these weights are randomly initialized, and then they are trained through backprop to uh, get the optimal value for these weights. So this is how we find the queries, this is how we find the keys, and this is how we find the values. In case of self attention, the only difference is all the input values are the queries themselves. So now we know how to find the queries, keys, and values. We apply our previous concepts that we used in the sequential network. What we do, again, we take the score, find the alignment score by dot product of query and keys, as I explained in sequence to sequence attention. Now we find the score for every word, as we did again in the sequence to sequence attention. Now that we have the score, what we do next is we just divide by under root dk in here, just a normalization step, which we did not do earlier. Next, we find the attention weights, as we did in sequence to sequence attention. We take the softmax of this 14 and 12, and when we found the softmax, right? These are the attention weights. What did the next thing that we do? We multiplied these softmaxes with the values to get the context vectors, right? Again, so at the last step, what we do is just multiply the values with these softmaxes to get the context vector, right? So there nothing is different. It is the same thing, only we are using weights instead of LSTM's RNN's hidden units. And in self attention, every input is a query. I hope the analogy is clear. So yeah, let's how I explained, we have an x, we have a wq, we multiply to get a q, x wk, we have multiplied to get a k, and then this for value. Now, since we have in matrix form, we can just easily write it in one step. What we always do is, multiply the query matrix with the key, and then divide it by dk. In this case, we take the softmax and then we dot product it with the value to get our context vector, right? So this is everything about the self attention part. It is very much analogous to sequence attention, only with two subtle differences which I explained. That's why I wanted to explain sequence to sequence attention in detail. Now the second thing that we wanted to know, like we know the encoder and self attention, but why multi-headed attention? What is multi-headed attention? So that's basically nothing. Like what they say is we have lot of attention heads instead of single attention heads. What it is saying is we do not want to have a single weighted vector like w q and just to get a single z, right? We have, instead of having a single w weighted vector for query keys and values, we'll have n number of vectors. For like in the transformer paper, they have used 6 attention heads, so they will have 6 weights like this, like w0q, w0k, and w0v, w1, and then so w2, w3, and w till w6, so on, right? So since we have 6 different kinds of weights, we will have 6 different kinds of queries, keys, values, right? So basically what we do is repeat the exact similar procedure of this, taking the dot product of query and key and then dividing it by root dk, taking the softmax and then multiplying it by value to get z. We do it for every attention head. We do it for 1, we do it for 0, we do it for 2, 3, 4, and 5, and 6. And we have the context vector from every attention head, right? We call it z0, z1, and z7, n number of attention heads, right? So we took single x, which was thinking machines, we passed it through every attention head, which calculated and gave us context vectors respectively, right? Now what we do is we just stack them. We concatenate all the attention heads, right? And then we have a final weight, which is called the WO matrix. We multiply this concatenated thing of all the attention heads. We multiply it with the weight, and we get the final context vector, which is then passed through the feed forward neural network. So why to complicate things? Why to have a lot of attention heads? The answer is a single word can have a lot of context, right? A single word can have a lot of meaning instead of just one. So what we are doing with a lot of attention head is we are taking a single input vector and we are projecting it into different vector spaces, right? Attention head 1 will project it into a different vector space depending upon what are the values of w0q, w0k, and w0v. Similarly, attention head 1 will have a different vector representation in space depending upon w1, w1 q, w1k, and w1v. So for every attention head, we will have a different vector space representation for every word, right? So in case a word has two different meanings at two different points in the sentence, our transformer knows, oh yeah, in that vector space, it has this meaning, in this vector space, it has this meaning. And so this word has a contextual meaning and we can grab that. That's the first thing. The second thing is it increases the ability of the model to look at different words, right? I know self-attention allows us to do that, but they say that it in self-attention it could be dominated by the actual word itself, and the multi-headed attention allows us to avoid that. So that is the main part between the multi-headed attention, right? So this is how the everything works. Putting it all together, we take our input sentence, we generate an embedding vector, we pass it through 8 different heads which have 8 different matrices. We find 8 different queries, keys, and values. We find 8 different context vectors. We concatenate them. We then multiply it by a weight which is also trainable, and we then finally get the final context vector which is then put into feed forward neural network. I know this is too much to digest, but if you have a look at it, just Jay LMR's post, you will now understand everything as as the sequence to sequence attention is clear to you, everything is a piece of cake. So now moving on to uh, the next thing, positional encodings, right? This will not be long, just a few minutes more. So as we know that we do not have LSTMs and RNNs now, right? We have only attention layers. So how do we take into picture the positions, right? Position of word, because sequence matters. When we were using LSTMs, they were sequential models, so they were automatically taking into context the position of the words, right? So how do we make the model understand that this word comes before this word and the position of this word is this and everything, right? So that's why we needed positional encodings, because we are not using LSTMs. So what positional encoding is basically a sinusoidal or cosine function. The intuition is that in the paper they say, I'll show you. Yeah, so in the paper they say, like when we use positional encodings, like when we use the sinusoidal function, the model will automatically know that the sinusoidal function is being used, and it will automatically know that from where this position is coming and from for what value of, let's say, x, this position is coming from. So that is basic intuition behind the position encoding. So next what we have is the decoder, which after understanding of the encoder is just a formality. Before that, I want to introduce the residuals. So going to the presentation, in the initial stages, we cut off these add and norm, right? Add and norm, right? So what are these add and norms? So if any one of you is familiar with ResNets, what we do in ResNet is we take the input and we skip the bit in between layers, and we just paste add it to the output of another layer, which we call it the skip connection. We do that to train deeper neural networks. What it is basically doing is, if the n layers in between these skip connection is not giving any extra information, we just skip it. So this concept comes from there, the residuals. We just take the initial embeddings which we had just before the self attention, and we take it and we just supply it after to the outputs of the self attention. We add it there, and again we do it the same uh, after the feed forward neural network. So this is basically the residuals. This is just to normalize, uh, just to normalize the in outputs, and this seems to give better results. I still have to find a better intuition for it. So here is basically what is happening. We have the layer, we have the x, which is having all the embeddings, and then we just add it to the z, which with the context vectors which we found from the self attention layer, right? So now the decoder. So what, again, like we in this figure we only see a single transformer, right? Like sorry, like we only see a single transformer. We had add and norm, and we had add and norm like here, and this is a single encoder stack, right? This is a single decoder stack, right? In that real transformer we have 6 encoder stacks like this, and similarly decoder stacks like this. So what the encoder feed forward output, it goes to all the 6 decoder, like the encoder output here, it goes to all the decoders. If there are 2 or 3, it doesn't matter, the output of these encoders will go to all the decoders, right? So what, like we have in the decoder, I'll explain. Just a second. I guess I have lost it, but yeah. So decoder, in decoder, we have the same self attention, we have the same feed forward. Only difference is we have an additional encoder decoder attention, right? So what this encoder decoder attention does is it takes the output of the encoder, and these become the keys and the queries for this encoder decoder attention. Sorry, keys and the values. What are the queries? So like we understood in sequence to sequence with attention, uh, the decoder model, the query was the output of the previous hidden state, right? So in this decoder encoder attention, the output of this self attention layer just below it is the query, and the output of the encoder is are the keys and the values for this encoder decoder attention, right? So I hope I am clear. Yeah, just to give a better understanding. Yeah, so the decoder side, as you can see, uh, we have the keys and the values from the last encoder. We pass it to the decoder, and so the self attention, the encoder decoder attention layer works just like multi-headed self attention, right? It's just the same thing, only the queries matrix are from the layer below it, right? And the keys and the values matrix from the output of the encoder stack, right? Just like we had in sequence to sequence attention, right? And the self attention is also similar to the encoder. Only one thing happens, like let's say the input is J, yes. Let's say the input is I am a student. So if the decoder is predicting for the word am, then all the words after am will be masked to minus infinity by the decoder in the self attention layer. So the decoder does not want the the self attention to look at the right side of the predictive the word which we are predicting, right? If we are predicting am, the decoder will mask the words after am to minus infinity, and it will say don't look at the right side, man. You do not want to get biased and just see at the right side and then predict what it is there, right? Because it is predicting the next word, and while predicting the next word, if we show the right side also, the decoder will already know what to predict. Just to avoid that, we add a mask to the right side, so the decoder only looks at the left side. That is the only difference in the self attention layer of the decoder. So now we have seen everything related to the transformer. So again, what we do is we take the input, uh, we have the input, we pass it through the encoder. The encoder does all its job, prints out a key and a value. It passes it to every decoder stack. The decoder then takes in the input, does all kinds of things which I've just explained, passes it through a linear and softmax, and then outputs the words. That is basically happening, what is happening in the transformers, right? So this was basically what the transformers are. And a very good exercise which I wanted all of you to do is, why, answer some whys. Why self attention? Why do we use self attention? What is basically it, what it is basically correcting on top of LSTMs? Why multi-headed attention? I already told you. Why positional encodings, embeddings? I already told you. Why residuals? I already told you. So I guess I'll tell the answer of why self-attention too in this presentation which I submit to KDM. But it is a good exercise to know why self-attention. So that was the presentation, guys. I hope I was able to explain. I'm not really good at explaining things, but I've tried my level best to explain whatever I have learned by my way, by reading papers. And yeah, and so I highly recommend this blog of J. Alamar. And after all this, just please go through the paper to have a very good understanding. And I hope it is clear. Yeah, Ion.
Yeah. So thank you so much, Tanul, for your high level overview about transformers, because this topic is not not that much easy, right? Because
Yeah,
this requires a little bit of your prior introduction to like these domains of transformers, or like you need to require at least the basic nitty gritties of these domain, right? So
true.
like I hope that you tried to explain as much as possible in the short amount of time. And like we have a few
Yeah,
questions. I will just share my screen, and let's see if we can answer those queries, right? So I will just share my
yeah.
screen.
I should stop
Yeah,
sharing, right?
yeah. You should stop sharing. So, are you able to see my screen?
Yeah,
So, like the first question was like, what is context vector and how it is generated? So, like, any insights?
yeah. So I told everything about that only. So a context,
Mhm.
like
No, no, yeah,
all
a
the
summarized
slides.
one, maybe
Yeah. So
that content.
a summarized thing is a context vector is can be different when we are talking about self attention, and it can be different when we are talking about sequence to sequence or encoder decoder attention. It's easy to make you understand what when we do encoder decoder attention, right? So the first step is to have a query. A query in encoder decoder attention will be the hidden state of the decoder. That will be a query. The second step is to have a key, which is all the hidden states of the encoder. And then what we do, we first calculate the alignment score. We do a simple dot product of keys and the queries to get the alignment score. We then take the softmax of the alignment score to get the attention weights, and then as a final step, what we do is just take the dot product of the attention weights and the values which we had in the first place. When we come to the transformers, what we have a we have three weights: queries weight and keys weight and the values weight. We create three vectors: queries vector, key vector, and value vector. Then everything is just easy to calculate the context vector. We just do simple dot product of query metrics and key metric. Then we divide it by root dk. We take the softmax, and then as a last step, we just multiply it with the value to
Definitely.
get
So,
the
like,
context vector.
uh so like this would be like even I think that there is a YouTube video on that too, like with some explanation regarding this. Like I'm not remembering the channel's name, but there is like if I remember, I will just post it.
Yeah,
So like I hope that it's like it's quite like easy and like it's quite doable, right? So like the next question is
yeah.
the number of hidden layers is the number of objects or words in the encoder sequence or in the decoder sequence.
So number of hidden layers, that would be a wrong thing to say. Like number of hidden states will be equal to the number of words in the encoder sequence. That's definitely true, right? uh, uh, like in case of when we are talking to sequence attention, that's the case. But with transformers, what we do, we just have an embedding of 512, and we have a whole different structure. So for sequence to sequence with attention, what we the number of words, the number of hidden states will be equal to number of words in the encoder sequence, not the number of hidden layers. Hidden layers are a whole different thing. So yeah.
So like the next question is how the softmax works. I hope that it was covered a little bit, but yeah, little bit insights.
Yeah, so the softmax is basically we what we do is just take the weighted average at last. Like you know what a softmax is, right? Because like what it does is just take the exponential weighted average. You can Google it. Like you will have a better intuition. What we do is just when we have the attention, like the alignment score, we just take the softmax. Softmax is a special function which I don't know. I cannot spell it because it's just a function basically. So what it does, it you can think of is just take the weighted average. Like if we have n number of things in the vector, then we add all the n number of things and we divide every individual element of the vector by that sum. That is the basic explanation, very basic explanation of what software. It's just doing weighted average, that's all.
Yeah. So like the next question is what paper is being referred. So I hope that when you submit the slides or like you can
Yeah, the
just
paper
add.
is attention is all you need paper. Anyone can have a look at it online.
So I would request a volunteer of ours to just put down that in the YouTube live chat so that they can get the information. And the next question, like maybe like we have like we will just answer the question till Sumit Kumar only. So we would not be picking up the questions after that. Okay. So the next question is multi-head attention weights don't have connections between them, right? So for a single key value, single embedding, would not gradient descent make the weights come to more or less the same minima? I hope that if you're able to see the screen, you can just maybe
Yeah,
make the same.
multi-head attention weights don't have connections. Yeah, the weights do not have a connection. They have a connection when we are doing the final, like when we are in when we have the context vector concatenated, we are multiplying with it with a final weight, right? The wo to get the final context, right? So that is basically the connection from the that weight is now connected to every weight of the multi-headed attention, right? Because z was the whole concatenated vector. Oh, okay, the question is between them. Yeah, so like from what I think is, what multi-headed attention is also a way to improve the dimensionality. Like they do not want the Google paper, like in the paper they say they do not want the, like they are reducing the complexity, so they do not want to lose context or to lose any kind of information. That's why they are doing multi-headed attention. So in that case, that's why they are giving a w0 at the end to multiply z with. So I think that will take care of it. And yeah, I think that will take care of it. I really don't know what is the exact answer to this question.
No worries. Like at least we got a kickstart, so it's good. Like yeah. So like, how do we like this question is like a bolder one. How do we decide if we should use transformers or not?
I
This is
think
a
you should
this is
use
a
it.
twin bolt.
I think you should use it
After listening.
because
Uh-huh.
I think transformers are very very much better than the previous approaches due to a lot of reasons. The single reason being, uh, they can gather the context of words which have different meanings much better than any other architecture right now.
So next question is the next and the last question is little bit your praise, like regarding your praise. So someone has seen your Alaska 2 notebook, which is very impressive. So like that's a compliment from that person, even to from the team of KDM. Like the
Yeah,
question is, how do you make a initial research on a very new data set? Because it's very tough for a beginner. Like they have a lot of new concepts to apply, a lot of new libraries they are not familiar with, which they might have to use right in the analysis of that data set. So how do you approach?
yeah,
So like I hope that that would be a perfect closing question
yeah.
for today.
So that is a very good question. Like what I do is just I first see a data set. Like whenever I get a notification that there is a new competition, I just go there and do every kind of analysis that I know of at that time. Right? I do not know anything. I just do, what's going to, what's the worst thing. Let's just do that. So I just analyze the data. I visualize some of the things and just I leave it there. Okay. So that is the first part. I do not write any kernel or I do not make it public, and then I wait for some grandmaster or some someone to publish something so that I can begin with. If they publish, then it's okay. Otherwise, in the meantime, I start to research. Right, I start to research what is, uh, like when you are doing something, right? When you are doing, let's say, when you are learning. When you are learning about something, like when you are learning cycling, what you ask yourself is, how do I ride a bike? Then you ask all the technical questions to yourself, right? What should I do next? Why this? And I try to ask every question which I have in mind to Google. I just Google everything, like why is technalysis, referring to the Alaska competition, what is technalysis, why do we do that, what is JPEG, why do we compress, and everything. I ask every possible question that I have in my book, and it takes a lot of days, but yeah, I have the solution at the end, and at the end I just summarize it and share it on Kaggle.
Definitely. So like that's the best approach we can think of, right? So thank you so
Yeah,
much for like taking out time out of your busy schedule and to just enlighten us about this like a bit advanced topic. Even like when it comes to transformers or other things, usually it happens that we try to get like proper setup, proper environment, that we devote a full weekend on learning transformers, right?
yeah,
So
yeah. I just
I
I just wanted anyone to understand sequence to sequence with attention, which is prior to the transformers. If you have a basic understanding of that, then only I guess you have a better understanding of transformers. But yeah, it cannot be. It is not something which can be understood just from a talk or something. Yeah, you'll
definitely.
have to dedicate time.
Definitely. So, like, I hope that your talk gave us the point to study on this weekend. Like, we have time
Yeah,
tomorrow,
I
and
hope so.
yeah, so like at least you gave us the kickstart, and now we will just continue and we will just study ahead, and maybe like be ready to get some LinkedIn requests, because people will just reach out to
Yeah,
you to get
definitely,
their
definitely.
queries answered. So definitely be prepared to get those things. And I really appreciate how you like it was really a tough task to cover all those things in a slide in such a short duration. So like I really appreciate your hard work personally, as well as from the entire team. And like, thank you so much for
Thanks
being.
a lot. Thanks a lot, and for inviting me once again and for giving me this opportunity. I
Yeah,
always wanted to share Transformers.
yeah,
People should
definitely.
know about it. Yeah,
Yeah, definitely. So like, I hope that we are done for the day, and thanks
yeah,
for like your insights. And if anyone have any suggestions, or if anyone have any queries regarding the talk, they can reach out to Tanul. And Tanul's talk and the slides or the research papers that he was referring to will be uploaded in the next 24 hours on our GitHub page. So do check out that in case you are looking for the slides or the resources that he was referring to. And this talk you can definitely refer to at any other time too, because it's on YouTube, and it will be there for like until it is public there, right? So like,
yeah.
definitely. So thank you so much, Tanul. And yeah,
Thank you, Ayan.
and yeah, thank you. And we
Thank
have
you,
a
Kaggle.
session. And we have a session on 25th of July on deploying machine learning models by Arghya Mukherjee, who is a associate director, at, let's say, like any like, I don't remember the name, but he's associate director of associate director at WNS Global Services. So he will be live there and teaching you about how to deploy machine learning models into real world. And I hope that this talk is worth attending. So I invite you all, and I would request volunteer to just put down the registration link in the live chat so that people can register. And thanks to all of you for joining. Signing off. Okay, bye bye.